Welcome to Rust Belt Science. I'm your host, Maggie Fink.
And I'm Shahir Rizk.
Today we have with us Michelle Thaller, who just recently retired as the Assistant Director for Science Communication at NASA, which is a very impressive title. You're an astronomer. You've done all kinds of things I won't list here because we wanted to use our time to hear you talk about some of them and some of your experiences with science communication for NASA. So welcome to the podcast.
Hey, it's great to be here.
Thank you so much for making time. You're here in South Bend visiting Notre Dame to give a lecture tomorrow evening for our Christmas series lecture. So welcome to South Bend. Welcome to Notre Dame. And you are also a fellow Rust Belter. You are
That's
from
right.
Wisconsin.
Yes, I grew up near Milwaukee.
Excellent.
So it's always exciting to have somebody from the region here to talk about science with.
Very exciting.
Yeah.
So what do we want to talk about, Maggie?
Well, the first thing we always ask our guests is just one question. Is there anything you are listening to, watching, reading right now that's interesting? It doesn't have to be science-y, just for fun, anything like that.
Well, sure, all kinds of stuff. But let's see. So, I mean, as far as the sciencey stuff goes, there is a video podcast series called Veritasium.
Oh, yeah.
Yeah, and so Derek Muller is somebody that I've had the honor of actually working with a little bit, and he's fantastic. And he just keeps coming out with things that go right to the heart of physics. Yes. But the way he explains them, it's understandable. It's very entertaining. So I've been because of a Veritasium recent podcast about entropy. I've been listening to other podcasts about entropy, trying to get my head around really what entropy means because it's very misrepresented and misunderstood. And so I've been doing that. What I've been reading, I just finished a book that was recommended on NPR called Paranesi, and it's a very interesting take on a kind of a fantasy novel. It has some roots as well in getting over trauma, but it was written so beautifully. Very simple but incredibly descriptive language. It kind of reminds me of the feeling I got when I read the Night Circus. That was another one that I read recently that I loved. So I've been kind of some fantasy novels and trying to get my head around entropy a little bit better.
That's a fantastic answer.
Hey.
Well, we are very big fans of Veritasium on this show. Also big fans of entropy. Yeah, I think you might be the third guest who talked about entropy in slightly different ways. So third in a row. So this has just been fantastic.
Because it's a theme, I think.
You're right. It is kind of misrepresented in the public. So the more we talk about it, I think the better.
Well, people seem to think it means disorder. And of course, it's so much more than that. Right. The last one I looked at was a video podcast where they were shaking a little box of pins. And there was a little bit of space, so like the pins weren't quite as long as the box, and all the pins lined up as you shake them. Yeah. And they were saying, well, doesn't that look like a more ordered state, right? Yeah. But somehow entropy is increasing while we do that. Yeah. And they were trying to explain that sure, all these pins kind of line themselves up, but that actually gives you more room at the top for a pin to be oriented in any direction. And so the entropy of the whole body is increasing. And it's also, again, it's something misrepresented. Sometimes people that are trying to detract from scientists will say, well, if you look at like the evolution of life or the universe, it seems like things are getting more and more complex. Right. But entropy is always increasing.
Always increasing, right?
It's one rule you just can't get around.
You can't break even.
Yeah, that's right.
Excellent.
Yeah.
Well, I want to get right down to it.
Okay.
And just ask the question that's on everybody's mind, right? Are aliens real, and where is NASA hiding them from us?
Oh, Lord. You really don't give us enough credit because, so most people that work at NASA, certainly not all, because it's a very diverse workforce, but especially among the scientists, we were all science fiction fans. We all are. Right. We love the idea of alien life. I mean, we were kids when Star Wars came out or, the next Star Trek. The first Star Trek was before my time. But, the idea that we somehow don't want there to be aliens, we really, really want there to be aliens. Yeah. The problem is evidence. Yeah. I mean, that's where it gets kind of crazy. So there's, as far as hiding them, that's always one that I really have to say I take some umbrage at because I actually don't think it would be possible for us to hide the existence of aliens.
Yeah. Absolutely not. Yeah.
And I want to give you one example, and this really did happen. I mean, somebody had asked me, like there's the Search for Extraterrestrial Intelligence, the SETI program, and these are the program is composed of excellent scientists. Yeah. So these are scientists that are very well trained in the scientific method and measurement, and they are scanning the skies looking for any signal that might be artificial. Yeah. Something that's very mathematical, something that doesn't seem to be just generated by nature. And there have been times when they have found something. But one of my favorite examples is there was an evening that they thought they detected something coming from space that looked very artificially made. And so people think the protocol is, call the U.S. government and have them lock down everything. No. Yeah. The protocol is, well, first what they do is that they actually move the telescope on and off the source to make sure that the signal isn't coming from their own instruments. It's some error that's in their instruments. Right. And then basically the next thing to do in the list of things to do is call everybody else in the world that has a radio telescope and see if they can confirm it. Yeah. And so this idea that there's a step in the process, like if NASA, if we discovered some evidence of life, that there's some official step that we need to get it cleared.
You mean movies are wrong?
Oh, Lord. Yeah. I mean, it's, obviously things have to be subject to peer review to say, but in the case of SETI, while they were busy calling people and going on and off the source, somebody in the network had heard what's going on and called the New York Times. Yeah. The New York Times was on the phone, I think, within about 30 minutes of this happening. Wow. The unfortunate to me, but because we never announced that we found alien life, it turned out to be a satellite that was malfunctioning and wasn't broadcasting at the frequency it was supposed to be. Okay. So it was in fact an artificial signal, but it was
human
artificial. Yeah.
Right.
And then there's the whole question about microbial life. I mean, so this is what NASA really searches for as a program. Yeah. We have huge missions, multi-billion-dollar missions dedicated to trying to find evidence of life either today or in the past. Yeah. On Mars, there are things we found that are there's so. Oh, it's almost kind of painful to be a scientist right now in history because there are things that are so tantalizingly close. Yeah. There are things that if we saw on Earth, we would say, I think that's evidence of ancient bacteria. Yeah. I mean, one of the classic ways we search for ancient life here is that biology can separate chemicals. And so you see chemistry that's been processed by something that digested it, and one of the things life does is it separates different kinds of carbon. Right. There's a heavier and a lighter form of carbon. The difference is just a neutron, right? There's an extra neutron. Right. Life likes to use the lighter part. It's actually easier to get to move in reactions and chemistry. Yeah. So one of the first signs we have of early life is what we call the sequestration of carbon, separating light carbon from heavy carbon in layers of rock or soil. And we do see that in some areas on Mars. Yeah. And so, but the thing is, we don't understand the Martian environment enough to say 100%.
Right.
I mean, but that's tantalizing.
It is.
So, I mean, all of the things are published. They're all public. They're all available for you to see. Yeah. But, right now we don't have the absolute smoking gun proof that it could be nothing but life.
And I think you can tell how cheeky my question
was. No, but it's a great question.
It's, I think that there's a misconception about, especially when it comes to things like aliens or even microbial life on another planet, that somehow we want to hide it as scientists. But of course, we all know that we're such big geeks that the first thing we want to do is just like, hey guys, check this out. This is what I found. And, that's exactly what we would want to do, is share everything. But you're right. It's so tantalizingly close that we can't really say for sure whether that's – but there's a lot of astrobiologists who are working on this.
Oh, absolutely. Yeah. It may turn out that some of these things we're seeing now we eventually will prove are from microbial life, but we're not there yet. Yes. And that's the thing. I mean, there's a possibility. I'm sure you've heard this. There's a possibility that in the atmosphere of Venus, there are there's a kind of light being absorbed from the atmosphere in Venus that here corresponds to high altitude bacteria. So bacteria that exist way up in our atmosphere. Yeah. Venus, the surface is horrible. It's 1,000 degrees. You don't want to be on the surface. But if life had just like on Earth, if life had started on Venus, then some bacteria could have gotten up into the atmosphere. Right. there's all of these things. There was even recently the tentative detection of a chemical on an exoplanet that possibly is a chemical that we know that is produced by phytoplankton. But again, I mean, scientists think that measurement may not have been good enough. Right. I mean, might not be real yet. So we're in this frustrating phase that some of these things may turn out to be alien life, but we can't say they are yet.
We can't say for sure.
No.
Yeah, I think it's interesting to hear scientists talk about some of these big, exciting possibilities and how cautious scientists actually are about the claims that they make. I think scientists are portrayed as kind of being deceitful, as, your question, people, where are the aliens being hidden? But a good scientist is very, very cautious about making really big and bold claims. And I don't think the public understands that so much, that what the scientific process is, what the scientific, what can we actually say about our data? And then, like, if a news source gets a hold of it, that's kind of that can lead to some of that more dangerous misinformation, especially when it comes to issues around public health. That seems to be a big problem. But even with outer space things,
and alien life,
there's all kinds of things that people believe are true that really have no scientific basis. But
I'm not sure how much people realize that how much this is a phenomenon of the United States. When I go and I talk to people all over the world, their first reaction is not, you must be hiding something or you must be misrepresenting something. And that's something that I'm kind of scared about, here in the United States, because we take for granted things like, there's a lot of gun violence and maybe they're hiding aliens from us. And people seem to think that, if there's an alien signal coming from space, somehow the United States would be the only one to detect it. I mean, there's radio telescopes all over the world.
It's the movies.
Yeah, well, of course, recently they had that wonderful series, The Three-Body Problem, which I'd been looking forward to for a while because I'd read the books. And there it's all centered in China. And it's it's a Chinese scientist that is the first to intercept a signal from, unfortunately, a not very friendly alien species. But I mean, we're part of a planet, and we don't own the sky. We don't own space. And if something is up there signaling or shining or whatever, we're not going to be the only ones to see it. There's no way to hide that.
And there's a lot of cooperation that goes on with different space agencies. And maybe our listeners don't know how much cooperation goes on between our space agency, NASA, and others throughout the world. Is that true?
Absolutely. Yeah. I mean, it's an honor to have worked for NASA. We are still by far the largest and most comprehensive space agency in the world. There's nothing else out there like it. But the James Webb Space Telescope are major partners. We're at the European Space Agency, the Canadian Space Agency. We especially for climate change and precipitation monitoring, Japan is a big one. Lots of collaborations with the United Arab Emirates, with Israel, with Brazil, with India. Every one of our major missions, like a James Webb Space Telescope or a Mars rover, every single one of those is an international collaboration. Yeah.
And that's wonderful because you get to really get perspective from very different scientists who may just culturally speaking, they think slightly differently from the way that we think here or over there. So, that must be amazing.
It is, and I think it's more important than a lot of people realize. NASA really takes its diversity of input very, very seriously. And I mean, that's pure game theory. There's actually good science behind it. Diversity of people that are going to give you different opinions, people that are different ethnicities or genders or ages or, live in different regions of the earth. All of that input actually can demonstrably mathematically give you a better result. Yeah. And so that's something people take very, very seriously. The international collaboration is something I'm so proud of. I mean, think about the James Webb Space Telescope, the best scientific instrument ever made for observing space. Yes. Anybody in the world can apply for time on it. Anybody.
Wow.
You don't need to be a scientist. You don't need to be associated with a university. Once a year, we invite proposals. Anybody can write a proposal as to what they'd like to use the telescope for. And yes, of course, when you're an astronomer that knows what you're doing, you tend to write a proposal that makes more sense. Right. But when you're accepted and the telescope takes your observation, you have 1 year to see that data just yourself because you won that proposal. And the proposal even comes with funding to give you time to analyze the data. And but then after 1 year, that data is completely public. Anybody can publish it. Anybody can see it. Anybody can publish it.
And can reanalyze it in their own way or however it is that they want to.
I'm sure there are Nobel Prizes in what we call archive data.
Yes.
Data that, I mean, just yesterday I was at this talk, and you were there too, where this man was looking at a globular cluster of stars fairly near our about 8,000 light years away from us, pretty nearby. And in the background of those stars, you could see distant galaxies that had never been detected before.
Yeah.
So think about that. In somebody's observation, where they wanted to see these globular cluster stars, somebody else could publish that, and they probably have, and say, "Look, new galaxies we've never seen."
Yeah, that's amazing.
Yeah,
and I want to go back to that application process.
Yeah.
So literally anybody could write a proposal and say, "Here's what's missing in the science, in our opinion, and here's what we would like to use the James Webb Telescope for," and my understanding is that the names are not included, so you don't know who is actually applying. The people who are reviewing the applications don't know that this person is a Nobel Prize winner or a huge-time astronomer or physicist. So this could be, myself, a biochemist. I'd have to read a lot of papers, and I could just, come up with if people think that this is actually worth it, then without looking at who I am, they would fund it.
Yeah, that was a big deal. So I mean,
that's a huge deal.
Yeah, I mean, this was the first telescope that NASA really tried this complete double-blind, no name on the review process. Yeah. And that was controversial because, I mean, there are people that would say, hey, look, I do have a Nobel Prize. I mean, doesn't that put me ahead in line? I know how to use the data. I'm associated with all these teams. Now, all of that should be included in the proposal in the sense that, you're working with teams of people. There's all sorts of, ways I have to use this data. You also have to be able to pick an observation that can be made. Yeah. I've worked with teachers a lot. And the teachers were actually granted some time on one of the telescopes I worked on called the Spitzer Space Telescope. And so this incredible world-class instrument had some hours dedicated for teachers to make their own observations. But they would start with coming in, it's like, I'd like to see two black holes collide. And it's like, I would too.
We all would,
So, I mean, the chance of observing that, you don't know when it's going to happen. They're just not easy to observe. So we had to really, partner them with scientists to create a proposal that could be done.
Right.
And so that's part of using these instruments.
That's fantastic. Yeah. To help people actually come up with the question to ask.
That's right.
Yeah.
A question that can be answered.
That can be answered or can be, that they can actually start to explore.
Yep.
Yeah. And that's really, a lot of science is about asking the right questions.
Oh, absolutely. Yeah. But also the question of where is the technology that we can answer this now?
Right.
And we have something at NASA called the Decadal Review. And this is run by the National Academies of Science. And they do international reviews every 10 years, hence decadal reviews. And they ask, like, all the astrophysicists in the world, what is the most important question that our current technology could actually answer? And that becomes a top priority for what NASA works on.
Because that's what the group essentially wants.
That's right.
That's what.
So there's a decadal review. Wants. There's a decadal review in Earth science, in the study of the sun, in planetary science, and then in astrophysics. Yeah.
That's super cool.
Wow. I didn't know any of that. As I've said on this podcast a few times, because we just interviewed an astrobiologist this week as well. So outer space has been on in theme, and I'm terrified of outer space.
Oh,
yes.
There's just the vastness of it. Like
it terrifies you?
Yeah, it just it makes me feel claustrophobic in a sense.
Yeah.
I don't know.
It is quite scary but fascinating.
Yeah, I mean, as I've talked to and learned more, I'm like, oh, that is really cool now. Like having some context other than scary movies or just staring up into the sky. It's just similarly.
It's overwhelming.
Yeah, similarly with like the ocean, right? That's frightening too. You just don't know what's there. Anything could be there because it's just so vast. So, but I'm like dipping my toes into outer space stuff now with talking to people.
It's all vast, and actually parts of it really are dangerous. I mean, people will say, I wouldn't worry very much about an asteroid hitting us. It happens historically. It'll happen again. But there are things that go boom out there in the night that you probably don't want to know about. I mean, there are these. We sort of recently in the last decades detected these gamma ray bursts that we now realize are giant stars dying, or two dead stars actually colliding together. But they create this burst of very high energy, very dangerous radiation, and even if you are light years away from them. There was one of these gamma ray bursts that happened 50,000 light years away. A light year is about 6 trillion miles. Right. And it actually blew the top of our atmosphere off. It actually had a noticeable effect of atmospheric loss from the Earth. And the Earth's magnetic field was like ringing like a bell for a little while afterwards. These events happen. And they travel at the speed of light. Yeah. So there's no warning. That's right. Yeah. So I mean, you don't see the explosion and say, "Oh, in 400 years that blast wave will get here." No, it's here. It's photons. It travels at the speed of light, and so I mean, those gamma rays could basically, in worst case scenario, like strip away an atmosphere.
Right. And but we had a close shave, is what you're saying.
Yes, we did, and we traced it back. We traced it back to this kind of dead star called a neutron star. Yes. And the neutron star had a little bit of a bad day, and a tiny little shift in its surface 50,000 years ago. And that blast got to us and had a noticeable, measurable effect on our atmosphere.
And we went, that was close. Yeah.
And now I stand by why I'm afraid of it.
Well, so you bring up neutron stars, which are fascinating.
Oh, my God.
They're supposedly they're super dense.
Oh, my God.
Super dense. Apparently, like one spoonful of a neutron star weighs as much as like Mount Everest or something like that?
Yes, absolutely. So a lot of people get all hyped up about black holes, and black holes are incredibly cool. But the problem with black holes is you can't observe anything about them directly because light gets sucked back in. And so you can observe material around black holes and falling into black holes, but you can't really say much about the black hole itself. And the thing about neutron stars is that these are monsters, almost as dramatic as black holes, but they're really there. Yeah. They're sitting there right in front of you, and you can see them. Yeah. And at NASA, we study hundreds of these things. So they happen when a giant star dies, and the core, which had nuclear reactions inside, keeping it sort of, supporting all the gravity of the star on top of it, the core all of a sudden goes out. The nuclear reactions stop. The star dies. And in literally just a couple of seconds, the layers of the star start to collapse down, and it compresses the core.
So gravity takes over.
Gravity takes over. And so if you have enough mass, nothing stops the gravity, and you rip a hole in space and time, and you got a black hole. Oh, okay. And just shy of that, if you have just not quite enough mass of all of those layers pressing down, you get this thing called a neutron star. And I really encourage people to go and see some of the educational videos we've made at NASA, because this is real data. We have an instrument on the space station called NICER. It stands for the Neutron Star Interior Composition Explorer. And
that's a cool resource.
That's right. And we actually can map what the surface of neutron stars look like. Yeah. And you have to be really careful when you map them, because you can see behind them as well as in front of them. So we look at this kind of distorted picture, and light itself is bent around the neutron star. It's sort of like you can see the back of your own head if light warps around.
What?
So these seriously, what? yes. So these things are about 20 miles across. Like you said, one teaspoon has about as much mass. To give you a sense, 20 miles across, about 2 times the mass of the sun.
Okay.
And 1 teaspoonful about Mount Everest. Okay,
this is much, much smaller than the sun. The sun is huge. We can fit I don't know how many millions of Earths.
Fit a million Earths inside. That's right, yeah.
And
20 miles.
20 miles is nothing. That's like,
Wow.
And that's the size of 2 masses of a star are in there.
Wow. And it's quite dense.
It gets to about twice the density of an atomic nucleus. Right. And this is this is basically a 20-mile across atomic nucleus.
Just packed together with basically no space between them.
It's amazing.
It's amazing.
Yeah. But these freaking things are real. I mean, you can take pictures of them. And when they have, little shakes and shudders, they can send out these high energy radiation bursts that can strip atmospheres off planets. And I think they're wonderful.
They're amazing.
But I mean, the time when I saw the data coming back from this was built on the same floor of my building that my office is, and when I realized the distortion around the edges was space and time bending around something 20 miles across. So,
wow.
you see behind it. And we actually use that distortion as a way to estimate the real mass of that neutron star. Because the more distortion, the more mass it has.
Right.
So, the more you see this kind of weird distorted edge, that's actually a measurement of what you can use Einstein's equations to tell you what mass must have done that.
That's what I was going to ask.
Yeah.
So is it correct to say that it's actually because of how massive it is bending space-time?
It is bending space-time.
Space-time.
It is absolutely correct. So when you think about it, I mean, light.
Wow.
So light has no mass. Light is just pure energy.
Yeah.
So gravity is something that affects mass, right? We orbit around the sun. We're two rocky, gassy things. But I mean, in the case of a neutron star, you get the distortion because space and time itself are bending, and the light has to go through space time.
Yeah.
As light goes through the universe, it has to travel through space and time.
Yeah.
And in a real set of data, a 20-mile across object bends space and time around it, and you can see it.
And so we're seeing what Einstein and others basically predicted. They said, hey, this could happen. And we're like, yeah, sure, whatever. And then here it is right in front of us. That's fantastic.
I mean, we've seen it before with stars.
With stars,
and with black holes.
Because they're massive. And they,
but it's like 20 miles across, and it's bending space-time around it. Wow.
That's cool.
Yeah, I'm a little less afraid now. That's, I think...
It's your friendly, handy-dandy neutron star. But
I just, astronomy, outer space is not a world of science I've really ever been a part of. So the more I'm learning about what astronomers actually are studying, and what information, what that's telling us about the world around us, right? It's like, oh, that is useful information. It is fascinating information. It's a world I'm not familiar with, and. So hearing you talk about it, I'm like, okay, I'm gonna have to go check it out. I need to go look at pictures of it and show my kids. And
the cool thing is, it's actually right around you right now. I mean, we some of the stuff that I see you wearing right now, you have some rings, silver and gold, and you probably use iodine. Like it's salt. Iodine is something our body needs. Things like that. Specifically, gold, platinum, and iodine are things that are made from neutron stars. So you actually have have neutron stars inside you right now.
That's awesome.
Our body chemistry wouldn't work. The only time we've seen, I think people are familiar with, stars are responsible for creating the atoms other than hydrogen and helium. That the oxygen that we're breathing right now, the carbon, the calcium that's in my teeth right now. The only way you make those atoms is inside a star. Yeah. For heavier atoms, for the things that are farther down the periodic table, like gold, silver, platinum, lead, iodine, bismuth, Pepto-Bismol, interestingly enough, the only time we've seen those elements produced in any quantity, a lot of the stuff, is when we've watched neutron stars collide with each other.
So they have enough energy or the right conditions, you could say, to make those heavier atoms in the periodic table.
Incredibly... colliding neutron stars, two neutron stars that used to be binary stars, they died, they both became these crazy little 20-mile balls of insane.
Yeah.
I was going to say insanity.
Yeah.
They'll come together, they'll explode, they'll create a massive explosion, and the heavier elements on the periodic table seem to be created more by that. So you have neutron star material. I mean, not neutronium, not dense as it was, but I mean, you have atoms in you right now, and your body wouldn't work right now except for neutron stars making that stuff.
That's amazing.
Okay, I feel like now I have found my connection to astronomers because I'm a microbiologist, and I'm like, we wouldn't work without the bacteria in our bodies.
Right.
And people are afraid of germs, and so I'm always like, no, they're really cool. We need them. They're important. All these fun facts. And then now, not only is the microscopic stuff, but all the macroscopic stuff.
Amazing.
All right, I'm on board. I'm on board.
So, in your body, our digestive systems, our neurons, I mean, they all take some of these heavy elements.
Of course,
and
we need things like molybdenum to survive.
That's right, we do. That's right.
Sure. Yeah. And so, as it turns out, the more we learn about something, the less scared we are of it. How about that?
There you go.
Awesome.
Yeah.
Good conclusion.
Good conclusion. But it's also a very good segue into your science communication work that you do. Obviously, we can keep talking about stars and stuff too. started this podcast because we think science communication is important. And obviously you do, and NASA does, because you work there as assistant director for science communication. So, you talked about some of the videos that are out there, some of the resources NASA has. What other kind of science communication stuff does NASA do specifically, and what kind of work did you do when you were in that position? And why is it important?
Yeah, well, I mean,
that's a lot of questions.
It's a tremendously huge enterprise. So, I mean, we're the only federal agency at NASA. I mean, and people sometimes forget we're a federal agency. We're part of the government. We're the only agency that, in its charter, which was written in 1958, the charter itself directs us to share with the public, share the knowledge of what we're discovering. And so, NASA has always invested in having really organized plans to work with school systems, to work with museums. There are people, I mean, each one of these is teams of perhaps hundreds of people across the agency that are trying to, make inroads into public schools or so that, I mean, there's all sorts of that outreach to the educational community, going to the conferences, trying to do things that support the curriculum in public schools. I mean, all of that. So there's a whole career path at NASA of working with tribal colleges or working with setting standards for science textbooks or whatever. So that's one part of it. There also, of course, is sort of the public leaning websites, the podcasts, the videos. I did more work in that area,
right?
And I mean that was just the best people in the world. Specifically, I mean they were all wonderful, but I spent a lot of time at the Jet Propulsion Laboratory, which is out in California near Los Angeles. And so we poached people from Hollywood that were amazing animators. It's like, working in Hollywood, I think I want to have kids now and have like a steady pay and health benefits. And so, I mean, the people we were able to work with as far as computer animators, people that could, direct the videos, live events, all of that. They're also, I mean, for me, there's something very important about even internal communication as a scientist to other scientists.
Right.
I mean, I don't know how many times I've gone to a professional astronomy conference or an earth science conference, and I have a doctorate in astrophysics, and I feel like an idiot. I can't understand
me too.
like 80% of the talks, right?
Yes.
And so honestly, what good are we doing our colleagues, by standing up, giving a short talk at a conference, and they just people usually just launch right into the details, right into the data. And even though I have a doctorate in astrophysics, because I'm not doing exactly your specialty, I have no idea what you've just said.
You get nothing out of it.
You get nothing out of it. And I even I took a stopwatch, and for poster sessions where people have posters on the board and you're trying to see what their research was, I spent so much time confused as opposed to, oh, I get it. I mean, it was like 80% of the time I'm just trying to figure out what they were wanting to research and why it was important. And so, I mean, I did a lot of work with scientists internal to NASA about how do you speak to your colleagues in a way that you actually really transfer information. I think a lot of people were just kind of afraid to admit that at conferences we're all kind of going from session to session going, I didn't understand any of that.
That was,
I think that's everybody's experience.
Yeah, I told my advisors, I don't think I'm dumb. I think people are not giving good talks.
Yeah.
Yes.
And when I realized that, I felt much more, the imposter syndrome went away. And I was like, oh, scientists don't know how to talk to other scientists very well, let alone the public.
And it's a hard thing to explain to people that are getting started in science, that sort of staring ahead at a lecture and nodding like you understand, but you actually don't, is what we're all doing together.
Yes.
And, it's sort of like the emperor has no clothes, right? At some point you say, well, how about we just make better talks?
Yeah.
I mean, and the stuff that you're doing, that's being done here at Notre Dame, I mean, there's some really excellent science communication training.
Sure.
And I can see the results of that. Also, I think, scientists had to propose to NASA, if they'd like to, I'd like to lead a mission to Jupiter. I want to be the head person on a spacecraft. All of that has, the massive proposals and team building. And at some point, you need to, stand up in front of a panel at NASA headquarters and basically sell your mission. I mean,
give a pitch.
Exactly, give a pitch. I mean, why should NASA invest? Why should the government? Why should the U.S. taxpayer?
Right, this is taxpayers' money, so we
invest
have to
in
be
your
very,
mission? And I mean, it's so painful because you get down to 10 missions you would love to do. Oh my God, I'd love to go to the moons of Jupiter, but I'd also like to go back to Mars. I'd also like to see a new telescope that looks at neutron stars. And so, you've got to somehow figure out how you're going to make that money decision. And if people can't communicate to the larger scientific community why their mission is important and why they should support it, they stand a disadvantage of getting that funding.
Yeah.
So there are real reasons internally to scientists as well. And so I've done those types of trainings too.
Yeah. It seems like you really enjoy it, and it's really needed. I think NASA is one of the most effective kind of science bodies at this science communication with the broader public. Even though I'm not in that field, it's kind of, I've always am hearing about NASA stuff. So probably thanks to a lot of your work as well. And I know my kids have dabbled in some of the resources, and I didn't even know it, and they were very excited I was talking to you today. So. Yeah.
I'm just thinking of all the teams of people we have that do this stuff, right?
Yeah, I can imagine.
Even social media teams, incredible science writers.
Yeah.
And they are the best people in the world. I mean they are working so hard for, you're never going to get rich as a federal employee. A stable paycheck is wonderful. You'll be fine. Yeah. But these people could be making a lot more money elsewhere.
Yeah.
And so I just have this incredible fondness for the people I worked with at NASA. It was the best part of the whole thing.
And I have to say, if you're out there and you're not following NASA on your social media account, do so. You don't have to be an astronomer. You don't have to be interested in astrophysics. You can. It's so approachable, and the images that are out there, and some of the jokes that they put out there.
They do put out some jokes.
It's really, really cool stuff. They seem to just you guys seem to be just having such a fun time with it, and what better thing to do than just have fun with the science.
I fight hard for that. I mean, there are some people that want that to be a more serious, sort of social media, and it's like, oh no, please put that snarky joke out there, please.
Yes, exactly.
Because people will respond to it, and it makes the science less intimidating.
Yeah. Oh, absolutely. I think we as scientists in my field, I feel like nobody's really having a lot of fun right now. But I'm in infectious disease, so that's not as maybe cool as stars. But this approach to science that scientists are having fun, and hearing you talk about stars, it's clear that that's just so cool and fun and interesting, and that translates and that makes people interested. And a lot of science, I feel like, lose that joy and that curiosity that they started when they became a scientist, and it's hard to keep it when you're trying to get funding and published and everything. So I think that's important to tell science. Let's not take it too seriously. Post that funny thing online.
Yeah, don't forget where you started when you were having fun with this.
I guess, for me, I wasn't perhaps a natural choice to become an astronomer because I like at school, the grades that I got the best grades in were things like the arts and history. And I got pretty sketchy grades in especially math. And in physics in college, I would say I mostly pulled C's, and B's in college in physics.
This is going around here, by the way. That seems to be the theme.
Yeah, but the interesting thing is people think that scientists this just came so easy to them,
right.
And because of that, for one thing, I hate this idea. Like, I walked in today to talk to a wonderful middle school, and the principal goes, "Oh, I want to stand next to a really smart person." It's like, not over here. The idea that you have to be somehow a different type of person.
Yeah,
you have to be super smart. What does that mean?
Yeah.
Yeah.
And for math, I love math, but it took me a long time.
Mm-hmm.
I didn't learn it quickly.
Yeah.
And especially when you're an undergraduate student, pulling a D in differential equations, which I did, it feels like your life is over.
Yeah.
It feels like you will never succeed.
Yes,
yeah.
For sure.
And so, this idea that it was easy for us, really what it was, just like you said, is I find this stuff fascinating.
Mm-hmm.
And there were aspects of being a scientist that did come easily, and there were aspects that did not, just like every other human being.
Yeah.
There were things that I was good at and things I was not good at. And so the idea that, mathematics and physics, especially the way it's taught in classes, just leapt into my mind. No. Mm-hmm. I had to struggle through that. But over the course of a career, it's become joy. I love the math, although as a professional scientist, you don't do much of it anymore.
Yeah.
You mainly write grants,
Yeah.
and you ask for money,
Yes.
and that is what the job is. Mm-hmm. But I couldn't get that joy of a neutron star or learning about the life cycles of stars. I couldn't get out of my head. Mm-hmm. And so my job, like everybody else, it's 80% budgets and applying for money and getting permission. It's maybe 80% not fun things, but I have a job. I was so lucky to have this job that 20% of the time was amazing. You're going to a launch or seeing the first images from the James Webb Space Telescope,
cool.
or 20% of your time is brilliant. But 80% of it is budgets and schedules and management meetings. And I think some people just don't realize that being a scientist is like being like everybody else in more ways than one.
Yeah, like everybody else. And then you got to go home and do the stuff that other people do.
Exactly.
Also at home.
Family, kids, housework.
Just normal people.
Feed the cat.
Yeah, feed the cat.
Got to feed the cat.
Got to catch up on reality TV and all the things. Yeah, and I similar to you, I loved chemistry and took organic chemistry and barely passed it, and now I'm teaching an organic chemistry lab.
There you go. Yep.
I wasn't the smartest, but I really loved it, and that can really drive you to do something that's crazy. Is go get a PhD if you love something that much. Because
and this idea that here I am standing next to a real smart person, that is already making science exclusive.
Yes.
And not really including people saying, oh, well, I can't be this smart. Because I know that a lot of people would say that. I definitely said that when I was a student, because I felt like, I wasn't getting the best grades. I was never a straight A student. And here I am, I'm like teaching students who are better than me in many ways. But at the same time, it's just that curiosity was always there. And I was lucky to have someone to say, yeah, that's not really the most important part. You have that curiosity, you have that interest, you have that drive, you have that joy when you're talking about this. Can you get people excited about it? So, yeah, absolutely. We don't want science to be exclusive, and I feel like, unfortunately, that seems to be what's happening.
Yeah, I was sitting next to a friend of mine that has a Nobel Prize, and as an aside, like two of my friends from college now have Nobel Prizes. It's like, what am I doing with my life? But this was Dr. John Mather, who's an incredible man, and we were sitting together at some conference, and somebody came up and said, "Oh, look at these incredibly smart people." And John turned around and said, that woman of color that's working 3 part-time jobs and trying to raise kids and trying to figure out how to survive. The amount of intelligence it takes to make that life work in any way, in any sense of it.
Absolutely.
We're so privileged to have the opportunity to have our jobs be exploring space, or all of that. The real intelligence is out there all over the place, and this idea that somehow, if you can do complex math, you're smarter than somebody that's, again, trying to figure out how to cobble a life together out of all these opportunities.
Yeah, I think it's really important for science to come out and say that. I don't think the public hears enough from us right now that
recognizing
I just tell people I'm just kind of good at doing school. Like, that's not really making me. I figured out that I'm good at taking classes, and
barely passing.
Okay, so maybe I wasn't that good at it. But I'm not smarter than anybody else. I just found the thing that I like doing, I'm very grateful to get to do it, because it is a privilege to be able to do something as crazy as explore outer space or look at bacteria under a microscope. So. I used to love, when I was working with the Discovery Channel, and I had that, I was co-hosting this television show. That's probably what your kids remember. But, I would take the subway in to work in the morning at NASA headquarters, and people would sit next to me if they had a question. It was actually really kind of lovely. There have been some not so lovely stalking incidents, but it was. But I would be sitting next to somebody that was doing like a food delivery, on the subway, and they'd say, "Hey, I saw the show. I wanted to ask you this," and I thought that was fantastic, about just the breadth of people that had watched the show and had enjoyed it, and had questions about astronomy, and I love that. Yeah. Well, my I guess he's almost 12. He has a question he wanted me to ask you. My son. Yeah. He wanted to know why we draw, when we're drawing stars, in a picture, why we draw them pointy, and what shape actually are stars.
Oh, that's wonderful.
I was like, I think that's a great question. So that is his question. There you go, Patrick, if you're listening.
That is a wonderful question, Patrick, because So you were at the talk last night when they showed the picture of the globular cluster. And did you notice that all the stars were spiky looking?
They were. They had this glare that went up and down, left and right.
That's
and sometimes, in 6 directions.
It looked like a 6-pointed star.
Yes.
And all, absolutely. Yeah. So stars themselves are like the sun. Right? The sun is mostly a sphere. And they're just so big that gravity pulls everything in the same direction, all towards the center, and what you get is a sphere. A
ball.
A ball. So stars are all shaped like that. The reason they look like spiky things in telescopes is that those are actually called diffraction spikes, and that happens when the starlight is really bright, and you're actually getting sort of it's basically bouncing off the support structures of the mirror in the telescope. So and it depends on I can recognize a James Webb Space Telescope image like that because I can see the shape of the support in there. And so I know this. So people started noticing this when we had big telescopes and we could take pictures, and a star would get overexposed. It's like lots of light coming out of the star, and you would pick up this bouncing of light off the actual hardware of the telescope itself.
Wow. Okay.
And we actually made a really nice info sheet, a really beautifully lovely cartoons about what those are. And so if your son wants to look up the James Webb Space Telescope diffraction spikes, yes. And then we'll have this wonderful, beautiful produced information about why. So every telescope has its own little signature that way.
That's really cool. It's like its own little personality that it imprints on the images.
Yeah. So the spikes are caused by the light bouncing off the support structures of the focusing mirror. Yep.
That's
all right. Cool. Wow, he did have a good question. I was like, I don't know. We'll see if what the answer is, because I was like, I don't know the answer, but. That is super cool. I wrote that down. We'll add it to the notes in the podcast as well, so other people can check it out. But thank you for answering his question. He'll be very excited.
Well, I want to play a game.
Okay.
I want to play a game. All right. So you are a native Rust Belter.
I am.
Yes. So you grew up in Wisconsin, the great state of Wisconsin, near Milwaukee.
Yeah.
So definitely a Rust Belter. So we're going to play a game that we call How Well Do You Know Your Rust Belt Home State?
Oh, no.
So we're going to ask you some questions about your home state.
Okay, here we go.
Of Wisconsin, and we'll see how well you do. I'll read the first question.
Okay.
Are you ready?
I'm ready.
Okay, so this is a multiple choice question.
Okay.
So Wisconsin is known as which of the following? Is it the land of 10,000 lakes? Is it the crossroads of America, or is it America's dairy land? It's an easy one.
Answer would be C, America's dairy land.
And that is correct.
The land of 10,000 lakes is Minnesota.
That's correct.
And crossroads, is that Indiana?
You are here.
All right.
Yes, you are here. Yes. So that's the first question. So you're 1 for 1. All right, Maggie, would you like to read the second question?
Yes, I can, but I don't know the correct answer because you wrote these down, so you'll have to. Which of the following was banned in Wisconsin between 1895 to 1967? A, French cheese, B, Italian mozzarella, or C, margarine?
C. It was called oleo at the time, and people used to make runs across the border to Illinois to buy margarine. I know older people that claim to have smuggled margarine into Wisconsin.
Talk about contraband in the state that is the dairy land of America.
I wonder if it ever actually happened that somebody was like randomly stopped by police and searched. It's like okay, got to give up that margarine. I mean, would they really take it? I don't know.
People in Wisconsin are so nice. I can't imagine
Oh yeah, you gotta take your margarine. Oh yeah, hard to say.
That's hilarious. Okay,
all right,
2 for 3 or 2
for 3. Okay.
So this
Last
is the final question.
I got this one right when I guessed.
You got this one. You were right. Well, let's see. How Michelle does. All right. So, which of the following is the official bird for the city of Madison, Wisconsin? Is it A, woodpecker, or B, a goldfinch, or C, a plastic flamingo?
Well, knowing Madison.
Yeah,
boy, I would love it to be a plastic flamingo. So the goldfinch or the woodpecker.
Or the plastic flamingo.
The plastic flamingo. I really hope Madison made it the plastic flamingo. Is it true?
That is correct.
Oh!
It is the plastic flamingo. It's a plastic pink flamingo. Apparently, it started out as like some joke, and then it took over, and now it's the official.
Yeah, the state bird of Wisconsin is the robin.
That's correct. Yes.
The state wild animal is the white-tailed deer. The state domestic animal is the Holstein cow. The state mineral is galena.
Galena, yes.
And the state rock is granite.
Granite.
Yeah. So I think those are the ones I remember. Having learned, I think fourth grade was all about like learn about your state.
That's more than I remember about Indiana. I love Wisconsin. I actually lived there for a few years out of high school. I went to college for my first degree up in Dunbar, Wisconsin. So very far north.
Close to the border of Michigan. Yes.
Yeah. I think
the Upper Peninsula of Michigan.
Yeah, the UP was the closest city to my college actually from where I was. So Wisconsin's great. And my PhD advisor is from Milwaukee as well. So wonderful people from Wisconsin.
Yeah, I mean, I always think, if you remember, a long time ago, the movie Wayne's World, where they meet Alice Cooper, and Alice Cooper talks about how great Wisconsin is, and it comes from Algonquin, or now we say Ojibwa language, and then he goes into the history of the socialist mayors of Milwaukee laid down this great system of parks and museums. It's true.
It is true.
Yeah. And so I was like, yeah, go Alice Cooper.
Yeah, go Alice Cooper. It is a beautiful state. Madison is a great town. Milwaukee's super cool.
Yeah. Well, now please come and visit me. So I'll show you bits of Milwaukee that maybe you haven't seen.
Very good.
That'd be fantastic. All right. We are out of time to talk about any more cool star stuff. But before we go, is there any last thing, fact, information, resource that you would like to share with the listeners that if you don't say it, you'll regret not saying it on this podcast that you want people to know?
Any final thoughts?
Yeah.
Well, we were talking, I do, NASA.gov is the website. It's really worth seeing. And one of them that I think is not really put forward enough is if you have any questions about climate change, about what we're measuring and what's happening, there's a website called climate.nasa.gov.
Okay.
And you will see exactly what we're measuring, right? I mean, not what anybody wants you to, politicians, no spin on it, nothing. Just what do the measurements say? And then there are other dedicated websites as well. Like there's one called exoplanets.nasa.gov, where you can track day to day. You will see the numbers change. We discover on the order now of 1,000 new planets a year going around other stars in the sky.
That's so cool.
And so they have a counter that changes day to day how many planets we know there are.
All right,
So like I said, those are two of the sort of subsidiary sites that I think are fascinating and very well done.
Okay, awesome. We will link those for our listeners so that they can check them out.
Thank you.
Great resources.
Yeah.
Thank you so much.
Yeah.
Great to be here. Yeah.
Yay. Thank you so much. Hopefully you'll come back to South Bend, or we'll come up to Milwaukee and we'll get to run into each other.
I would love that.
Okay. Yeah,
awesome. For sure. Thank you so much.
Thank you.
Thank you.
At the end of our show, we would like to thank you, our lovely listeners, and our awesome audience for spending your time with us. We thank the Notre Dame College of Science and the Indiana University South Bend College of Arts and Sciences. Special thanks to the wonderful people at the Notre Dame Studios. Coming to you from beautiful South Bend, Indiana, in the heart of the Rust Belt, this is Rust Belt Science. I'm Shahir Rizk.
And I'm Maggie Fink.
And we'll catch you next time.